experiment. I'm not sure how it's going to go. I'm not sure whether we have more bar or less. We can work that out next time. This last section is a bit of an experiment. I have no idea how this is going to go down. Ben Jones is terrific, but I hope it works. All history starts with geography. So I thought we ought to start off by looking at the geography of the Coal River Valley. We're here, after all, to talk about the foundation of a bridge which was there to cross a river. There's nothing more obvious in historical and geographic terms than that. And why that came about, hopefully Ben Jones will address. Ben has got an honours degree in science and a Master of Economic Geology from UTAS. He's a geologist and resident of Coal River Valley, as I'll point out. Since graduating here, his geological career has focused on, easier if I can read it, mineral exploration for gold, copper, zinc and lead, whilst also maintaining an interest in engineering geology. Ben has worked around Australia, including Antarctica, and Ben and his wife Hannah together run the 340 hectare farm Daisy Bank, which I think most people will know on the western side of Richmond, where they offer farm accommodation and grow wool, lamb and vegetable seed. The Jones family have owned and managed Daisy Banks since 1896, and of course I was referring to Richmond crossing place is Ben Granlund. Ben, please welcome Ben Jones.
Thanks very much for the lovely introduction, Alan, and inviting me to speak tonight. I've never spoken with two screens, so excuse me if I start doing this a little bit too much. Firstly, I'm not an expert on the Coal Valley geology. As Alan said, my previous experience has been in mineral exploration. When I left university, I took a job at the Beaconsfield Gold Mine as an underground mine geologist, and then over the next 20 odd years my working career took me further and further away from mines and into mineral exploration and the search for new mines. So you may say I'm a bit of a generalist, but I've lived here on the farm for almost 30 years, which gives me a bit of a local insight. Enough about me. I've tried to keep tonight's talk interesting, linking what we see around our homes with the previous geological events. So, get started. As Alan pointed out, geology and history have much in common. Only geology looks much further into the past. Just as historical events of the past tend to repeat themselves, the same applies for the current landscapes and rock formations that the same applies for the study of geology, only that the geology works in reverse, using the current landscapes and rock forming processes to estimate what happened up to 4.5 billion years ago. I want to touch on the previous work completed in the area by government geologists before starting a tour through time, looking at the major elements that make up our valley right up until what we see outside today. For each rock formation, I'll outline how the various materials have been used around the Coal Valley, and my apologies for those from the upper reaches of the valley, because much of my talk tonight focuses on the area around Richmond, where a lot of the examples in geology principles are just easier to describe. The earliest written records are of an exploration party that came from Risdon Cove and found thin seams of coal just below the current weir in Richmond. That was back in 1803. Leading on from that initial discovery, two separate mines based up around Coalbrook produced coal up until 1919. Unlike large coal fields, the seams were both narrow and of poor quality, and hence no further activity. The first modern geological map was completed in the 1960s, and since then, much more detailed mapping has been done around the year 2000. I'd like to introduce the geological timescale to help keep the various formations in context for the talk, and to make it a bit easier and help you know how close you are to the end of the talk, you can trace your time along the bottom. This isn't the most recent geological map, but it's a nice simple illustration of the area between the lower reaches of the coal up to north of Campania. It was made by one of my old lecturers at uni, Dave Lehman, who was a government geologist in the 1960s and 70s. I like it because it has the main elements of the valley without the detail not relevant to tonight's talk. Looking at the map, we already see the similarities with the topographic map, where where we see, this is an interesting drive, I might just walk over here and talk about it. We see the major hills, it's the topographic contours, and the valley floor here in brown and yellow. The hills are dominated by the Jurassic dolerite, and the valley floor, the brown and yellow colours, are dominated by the more recent sediments that make up that area. Going back to the oldest rocks that outcrop in the Coal Valley, Permian sedimentary rocks, they were formed in a marine setting, so think about something off the coast of Tasmania where you've got sediments forming in a relatively deep setting. This time on Earth was generally cooler with a lot more glaciation. An easily recognisable feature of these rocks are drop stones. So drop stones normally are made of something different than the rock that they're hosted in, and they represent erratics of glacial moraines where an iceberg has melted out at sea and dropped that rock down into what was otherwise a very regular, benign environment. So you may find those, particularly down at Huon, where there's a lot more of those rocks outcropping, but if you find a small piece of quartzite, it doesn't look like it belongs in that place. That's probably where it came from. Permian rocks in the Coal Valley are quite rare. They're rare partly because they consist of finer grained sediments that are not as resistant to weathering and erosion as the coarser grained sedimentary rocks. I'd like to start, before talking about sandstone, by quickly introducing what happened at this point in time, with time being between the Permian and the Triassic. There was a massive volcanic eruptions in current-day Siberia, which released a large amount of CO2. The dissolved CO2 in seawater acidified the oceans and produced a lot of acid rain. Think of a Queenstown before better environmental practices. Not much survived at that time. It was a major extinction event. Unlike the older Permian rocks, the Triassic period rocks formed in a freshwater environment. It is important to note that from this time on, the Coal Valley area was above sea level. So it's important to think maybe 250 million years of history, we haven't had sea under our feet. They probably formed in a large river delta setting, something probably most akin to the Amazon. We don't have anything around Australia that's equivalent, but braided rivers, lots of sediments that lie. It would have been a pretty benign sort of plain, not much topography. As time went on, continents started to form into something close to what we see as the supercontinent Gondwana. You can see the shape of Australia down at the bottom of that figure. Looking around Richmond, the subtle hues of the Triassic sedimentary rocks dominate the Richmond area both as prime building materials and the hills around us. So this is just a Google Earth image looking out towards Mount Wellington in the far background with the Triassic sandstone outcropping on Butcher's Hill. Not all sandstones are the same. And just as soil scientists will argue about whether something's a clayey sand or a sandy clay, geologists also tend to divide their rocks into different formations. Fine-grained and sedimentary rocks are typically more clay-rich and therefore tend to erode away more quickly and become recessive in the landscape. So when I say recessive, I mean something that's not going to present on a hill. They tend to erode away, and it's the harder things that remain. Coarser grained sedimentary rocks, such as those of the Triassic, contain more quartz, which is both chemically and physically resistant to weathering. Put simply, hard rocks stick out while the soft ones and finer ones erode away. looking at the profile of Butcher's Hill, we can see the steeper slopes represent the coarser grain, more quartz dominant parts of the sandstone, whereas the more gentle slopes that are flatter tend to be the finer grain rocks, and they simply erode it away back to that profile. There's some excellent digital elevation data available for free for people that like playing with maps. LiDAR is being used a lot for flood modelling and coastal inundation studies. But I chose this graphic just because it's an excellent reference of the old quarries on Butcher's Hill, which is the believed source for the bridge, which we've talked about quite a bit this evening. And the little bit of research I did suggested that the stone for the bridge was drawn from Butcher's Hill by convicts by hand, no bullets. In the quarrying of the stone, it's important to remember that not all the material is the same, and the quarry operators would have looked for stone that was free of features and less likely to erode away or fret to make something that lasts 200 years, as we were saying. You jump out of the Triassic sedimentary rocks and into the Jurassic. This is a major feature of the coal landscape. Jurassic diorite intruded Tasmania approximately 170 million years ago. These rocks are rich in iron and magnesium, being sourced from below the Earth's crust in the mantle. The diorite intrudes through weaknesses in the sedimentary formations as the crust is under extension via feeder dikes. It then inflates the stratigraphy to form flat-lying sills that really mirror the existing rocks. Probably the easiest way to think about it would be squeezing mayonnaise into a sandwich that you've already made. So it really just parallels what's there already. Diorite's very common across eastern Tasmania. So when you look at the map again, you see that a lot of the colour there is the burnt orange colour of the diorite that forms the main hills along the western side of the coal valley. Jumping a bit further up the valley behind Nocton Vineyard, looking back down towards Richmond above the quarry there, we can see that the Jurassic diorite can form multiple sills rather than just one intrusion. This photograph that I've coloured in, looks like a 5-year-old's coloured in now on the screen. The orange just represents the diorite. You can imagine the rocks dipping back out towards yourselves, and the green represents the Triassic sedimentary rocks. And the quarry sits in the middle there on the contact between the orange and the green. Because the sills are still greater than 1,000 degrees Celsius at the time of intrusion, the diorite can strongly affect the surrounding rocks. Internal changes are also seen within the sills, with smaller crystals and more fractures near the margins, and larger crystals with fewer fractures in the centre of the diorite sills. As I said, diorite's rich in iron. When fresh, it's a dark bluey grey colour and is used extensively for road aggregate in eastern Tassie. When weathered, the diorite forms a red gravel that we see on our country roads. Onion skin weathering of uniform materials such as diorite is common in a number of other rock types. For people that travel up the east coast, you'll often see granite tends to weather in the same way to produce what we call core stones. This is one of the reasons why you can still find heavy, fresh diorite boulders in your soil when you're digging around your garden or on your farm. These are simply the last part of the diorite to weather away. At Nocton Quarry, the Triassic sedimentary rocks above the diorite are baked by the intrusion. This stone presents a very hard stone, so if you can imagine it's been baked as if it was in a kiln, and it also forms a number of fractures, which makes it ideal for stonemasons to build things from, which is what a lot of that light coloured material on the screen is used for now, if it's not crushed to make a decorative gravel. It's a good photo when you can use it twice in a talk. Excellent aspect aside, the premium wines produced from the Belmont Vineyard owes much to the quality of the terroir. Black cracking clays develop as colluvium weathering from upslope and forming a veneer over the more free-draining Triassic sandstones. So if people can understand, the orange at the top of the illustration is the Jurassic dolerite on top of Butcher's Hill, and just over the time, the different elements of the dolerite have weathered, and through wet times and with the help of gravity, that material just creeps its way down the slope and forms the topsoil that we see underneath the Pooley's vineyard. The calcium-bearing mineral in the dolerite called cyanopyroxene breaks down when exposed to air and water to form a carbonate mineral called travertine. This carbonate is commonly found at the interface between topsoil and rock, and its natural neutral pH is excellent for viticulture. Stepping out a bit more at a bigger scale, the intrusion of the dolerite 170 million years ago marked the beginning of the Coal and Derwent River alignments. From this time on, the rivers drained to the southeast. Crustal extension relating to the breakup of Gondwana created the weakness in the crust for the intrusion of dolerite across Gondwana. The resultant landscape would have previously resembled undulating plains, then became blocky with a strong north-west alignment. The long period of erosion followed the intrusion of the dolerite. Erosion of the overlying sediments reveals the recessive dolerite which caps many of the hills around eastern Tasmania. The beginning of the Cenozoic was a big show. It started with a large meteorite impact in present-day Mexico that caused the most recent mass extinction event. Collision of a 5 kilometre diameter meteorite into shallow water in the sediments likely created a lot of dust, a vast amount of dust that went into the atmosphere, blocking the sun and producing a prolonged winter around the globe. 75% of species present at the time became extinct. Further east-west extension, so extension, we're just talking about stretching the crust, led to the development of horst and graben faulting, responsible for the form of the coal valley we see today. Looking at the figure, it's not difficult to visualise driving into the page along the bottom, looking over at the Coal River Cheer to your left as you drive to the north. No good story is complete without fire and brimstone. In the previous slide, we talked about how continued crustal extension led to the development of the horst and graben faulting. Continued extension led to the second phase of igneous rocks in the Coal Valley, this time as lava rather than the intrusion of sills. Basaltic lava tends not to produce large volcanoes or explosive eruptions with massive columns of ash. Instead, small volcanoes and fissures are the main source of lava. Lava fields in Hawaii are very similar to probably what the lava looked like in the Cenozoic Coal River Valley. There's no difference between the major element chemistry of a basalt or a dolerite. Basalt is simply an extrusive variant of dolerite. Basalt underlies much of the Coal River Valley floor, as shown on the map in the orange colours. The main vent was located near Ladina Orchard, just to the north of Campania. There were several other volcanic vents in the area to the east and to the west, but this is just a neat example of what was probably a very significant fissure or vent that then went on to fill the valley. Basaltic lava has a very low silicon and aluminium content, and that doesn't sound particularly interesting in itself, other than it means that lava has a very low viscosity, allowing it to flow very freely down the established Coal River Valley, as illustrated by the dashed arrow on the screen. And you can't get away from home to take a photo, you can always use Street View. Basalt presents in many forms. Given more rainfall, temperature and resultant weathering, it can produce some of the best soils in the world, such as in West Gippsland or on the northwest coast of Tasmania. However, in its fresh condition, it's resistant to erosion and therefore can be a strong influence on the future landscape development. Part of the Richmond bypass was constructed using crushed rock blasted through this section of basalt just to the northwest of town. The majority of the Coal Valley north of Richmond is developed in Cenozoic sediments. Sedimentation of silt, sand and gravel continued before, during and after the basalt lava flows. Drilling at Carrington, just north of Richmond, revealed greater than 200 metres of sediments below the basalt lava. The traditional fence lines often map out the contact between shallow rocky soils developed on Jurassic diorite and well-developed soils suitable for intensive agriculture. The same pattern of historical land use can be seen across Tasmania. National parks are found only in areas left with native vegetation that man could not pull through a plough. This reflects the earlier settlement of white man and much later setting aside of land for conservation. I've not talked about the groundwater so far. Studies suggest the Cenozoic sediments and basalt represent a reasonable aquifer. That work was really done back in the 1960s. However, the water unfortunately is too salty for general use. Examples of saline groundwater are common up Pages Creek catchment and also around the Nocton Vineyard near the main road. Reasons for why the groundwater in these shallow sediments is salty is probably due to windier times, possibly during glacial events, when it was much windier and the salt essentially was transported from the sea and laid down on the land and then buried in further sediments, making the resultant groundwater more brackish. Now move on to the most recent and superficial geological formations in the Coal Valley. These sediments are formed in the last 2.6 million years. This image is a combination of the LiDAR that we looked at before with the most modern geological mapping. And zoomed in at Richmond, we can see that there are a lot more letters and domains of geological formations that have been mapped by the geologist around the year 2000. The colder colours represent the low-lying areas and the hotter colours represent the higher elevation areas. On this map, the youngest rocks are represented by the Q prefix, and where there are more letters, the geologist has had more confidence in what the origin of those sediments were. Probably the easiest thing to draw your eye to is that the bluer colours, so the lower lying areas, are dominated by Quaternary sediments, whereas the remainder of the valley floor, both in the centre of Richmond and as you move out to the north, are dominated by the Cenozoic sediments that we were just talking about earlier. Pinch points in the Coal River exist just below St John's Church and at the Richmond Weir, which represent where flood levels can rise most quickly. I guess from a flood management perspective, that means keeping those areas clear has a bigger impact than other areas in the valley because it's a natural dam. As I said earlier, detailed flood modelling of the Coal Valley and also coastal inundation modelling of coastal areas around Tasmania relies on this sort of data. The last glacial maximum was approximately 25 to 20,000 years ago. Sea levels were approximately 110 metres lower than they are now, owing to the volume of water held in ice at the poles and glaciers. The central plateau of Tasmania was covered in ice. Tasmania was connected to Victoria via a land bridge, permitting Aboriginal people to walk freely across. The cold period in history was also very windy. High winds accumulated sand deposits around Tasmania. In the Coal Valley, these are preserved around Malcoms Hut Road as localised deposits, and north beyond Richmond, where in some places you can still make out sand dunes. Several of the large shallow lakes, such as Lake Tiberius and others further to the north as you travel up around Ross and Campbelltown, represent areas where the wind has eroded the landscape rather than deposited sand. Alluvial fans then represent short transport and settlement of sediment on the valley floor. They are really the last sediments that you see in the Coal Valley and represent periods of higher rainfall where material has come down a valley and simply run out of momentum and deposited on the otherwise flat valley floor. I want to speak briefly about landslips. Landslips are relatively common on soils made mostly of clay. In wet years, when the clay is saturated, the cohesion, or think of it otherwise, the stickiness of the clay is at its weakest. On steeper slopes, the shallow soil detaches from the weathered bedrock and moves down slope under the effect of gravity. These features are most common on some of the aspects of hills where the evaporation is also at the lowest. This photograph in the bottom left corner was taken above Red Night Orchard and just illustrates a very recent landslip in the last 3 years when we've had La Nina cycles, and we see older versions of those as people that look out the window up towards Colebrook. There's quite a few on the slopes as you meander your way up Mudwalls Road. So, in a nutshell, Coal Valley probably formed 170 million years ago in its current alignment. Sedimentary rocks and intrusive rocks dominate the folded hills. Basalt lava flows and sedimentation filled the Horston Graben folded valley over the past 40 million years. And current sea levels and climate have prevailed since the end of the last glaciation event, approximately 12,000 years ago. That's all I've got to say tonight.
These lava flows, I sort of picture volcanoes these days seem to sort of go up every now and again, stop, and then back at that particular period of time, are we talking these volcanoes later, as you say, the fish or would that have been would that have just been erupting for thousands of years? Or
yeah, probably millions. So
millions.
The most recent ones I think were dated around 2 million years old. So not that long ago in the scheme of geological history. Yeah.
So it's a long period.
And as you move out towards Tea Tree, I think there are some great examples of small vents where you can still find the volcanic bombs that have been thrown out from the vents. But volcanic products aren't very well preserved in history because they cool quickly. Often they can be eroded easily, and so only the most recent or in areas that have been protected for other reasons are preserved.
I'm intrigued to know what it was that Governor Arthur looked at specifically at Carrington when he set in the soil, when he actually wanted that farmer.
Good question. I guess with my farmer hat on, I'd say access to the river, and when you look at the cadastral boundaries, they often work at a tangent out from the coal, like a lot of early land planning. So access to a nice stretch of the Coal River and flat. I mean, I gather it was his undertaking at Carrington that led to the original road coming over, that's my understanding, over the hill from Risdon. So I don't think there's anything particularly specific about the soil or the geology there. Perhaps just that part of the river you took a shine to. That's all I could think.
May I make a suggestion? I didn't follow Alan's advice and record this. I'm really irritated at myself. But when I was first reading about some of this, there was that 1803, I think it was Meehan coming across. Two things stuck out from that. He was staking out with survey pegs, which tells me that you'd only, you do that if it was relatively open. The Aborigines were following him around, taking the pegs out, which I thought was amusing. It ended badly, of course, but they were five-stick farming up through here, and if you were choosing which land to go for, everything you said, plus the openness, that had come from the way the Aborigines had traditionally maintained it as hunting grounds. So it was probably some combination of all of those things.
Probably similar to the landscapes that are described in central Victoria when pastoralists first went there. Aboriginal land management resulted only in grassy woodlands, so it was very amenable for people to unload their sheep and start chewing away. There are a lot of references to tea tree in the district, and yet I can't think of a naturally occurring tea tree left, which makes me think that probably a lot of the creek and river floors were dominated by tea tree. But much the same as the comment about where you find national parks, because the land was the best for farming, probably all that original vegetation was cleared a long time ago.
Well, David Beeman was great, you mentioned David Beeman before. He always said that different geological areas provide different botanical.
Yes.
Which is actually a really interesting connection, especially for Indigenous people.
You can map the different geology by the Euclid, for example. The mean range with Risdonii, the rare Euclid there that grows on essentially rock and gravel. You don't find that growing on diorite, for example.
I'd like to start something also. Did you say 10 to 15,000 years ago this area was under water?
No, so the peak of the last glaciation was around 25,000 years ago, but by the time we came to about, I think it was just under 13,000 years ago, that glacial maximum had come to an end. So essentially, walking out the door now...
Is that climate?
Well, it's mostly driven by what they call Milankovitch cycles.
Right.
So it deals with, and anyone who's an expert, correct me or stand up and shout. Essentially, it's dealing with the Earth's wobble and its axis and where it sits with reference to the sun. And there's a certain periodicity approximating 20, 40 and 80,000 years that dictates basically when we see glacial events in Earth's history.
Ah,
Yeah. So
not one of those wobbles.
we'd actually due for a glacial event. If you speak to geologists, that doesn't mean you shouldn't live your life gently.
Nothing to worry about.
Yeah.
You give Ben a hand, please.